Given a group template, there are two questions that immediately come to mind. First, is the template valid? And second, if it is valid, does the template define an essentially unique group? Now, one approach to showing that a template does define an essentially unique group is to show that the template uniquely determines both the underlying set and the group product, as we did in an earlier example, 6.21. And that tells us that there's at most one group satisfying the template, so we then need to actually find such a group. And this is the approach I'm going to take when we talk about the next subject, standard templates. This is really the motivation for defining templates, I think, for this course anyway. It's the standard templates that will be of the most interest to us. So, one of the most useful families of templates is given by this specification. I'm going to use the notation MNT, little t, specifically for standard, what I call standard templates. Two generators, order of A is M, order of B is N, order of the group is the product, Mn, and we have a basic commutativity rule, BA equals A to the TB. So for want of a better name, I'm just going to call these standard templates. Note that if the integer t is not in the range 0 to m minus 1, corresponding to the order of A, then we can replace t by its residue, mod m, without altering the template, so we can assume that t lies in that range. And as we have discussed, if the standard template is valid, then the t condition must hold. And this is what the t condition looks like. It's t to the order of b, which is n, congruent to 1 mod order of a, which is m. Now in general, as we've already seen, the t condition is necessary for validity but not sufficient. However, for the standard templates, it is sufficient. And when the t condition holds, or equivalently when a standard template is valid, it defines an essentially unique group. So to see that, let's assume the t condition holds for a standard template. And the approach here is a common one. We'll assume that, for the moment anyway, that there is a group G that fits the template, and we'll see what we can learn about G, and hopefully we can turn that into necessary and sufficient conditions. So G has order Mn, and its underlying set looks like this. Remember, we can restrict, we can use the commutativity rule, where'd it go? There it is, to move all the A's to the left and the B's to the right. So all the words over AB look like this, and we can restrict to these ranges because of the order of the generators. And now this gives us Mn distinct elements, which therefore must constitute the entire underlying set for G because it has order Mn. And we've also seen that the group product looks like this. We use the generalized commutativity rule to collect all the A's to the left and all the B's to the right. Oh, I'm sorry. Okay, there we go. So, assuming that G exists, the template uniquely determines both the underlying set and the group product of G. This shouldn't be here. Now, to find a group that fits this template, we can use what we have just learned the T condition, the underlying set, and the group product of G. We can use these things to actually construct an abstract group that fits the template. So we begin by assuming that the T condition holds, and then we define this set of distinct formal symbols. I ranges from 0 to m minus 1, and j ranges from 0 to n minus 1. Now these are formal symbols. This is not a product. It's not juxtaposition. Well, technically it's juxtaposition of formal symbols, but don't think of it that way. This is just one symbol. A to the I, B to the J is a single symbol. You can't break it apart. And we're going to use a little bit of notational convenience. We'll denote A to the 0, B to the 0 by 1, and so on, the obvious things here. So we have the T condition, and we have a set of abstract symbols. Now we want to define a product on G. And we do it to be consistent with the product formula that we saw must hold if G is to satisfy the template. And so it looks like this. So this is the same right-hand side. I put an asterisk here because we are defining a binary operation, and I don't want to just use juxtaposition because it'll make it look like these are also products, which we just got through discussing. These are formal symbols. They don't break apart. They're not products. So what we have to do now is prove that this underlying set with this binary product is in fact a group. Well, the identity element is clearly A to the 0, B to the 0. Associativity is a little bit trickier, and it will help to make an observation first. And I know why we need this observation because I've read ahead. So right now it's going to seem like this just came out of the blue, but you'll see in just a minute why I want this. So take any integer u divided by the order of b, which is n. Get a remainder between 0 and n minus 1. Now the T condition implies that T to the u equals T to the Qn plus R, which can be rewritten this way. And now if we're going to take residue classes mod m, T to the n is 1. So this is just T to the R. And R is U mod n. So under congruence mod m, if you look at the first item, T to the U, and the last one, T to the U mod n, we can remove mod n in the exponent of T as long as we're taking congruence mod m. Now we're ready to look at the associativity law. So I've got 3 integers here between 0 and n minus 1, 3 here between 0 and n minus 1. This is associativity in one direction. So I am first you perform the product of the first 2 elements, then you take that product with the third element. So how do you you just use the product formula. So I need to move this b to the j across the a to the k, and that will cause k to be multiplied by t to the j. So this is a to the I, because that's already here, plus kt to the j from moving this across, and then reduce mod m. That's part of the definition of the product. The b to the j goes across to b to the l, so it's b to the j plus l. Again, mod n, because that's also in the definition of the product. Then we have to multiply by a to the x, b to the y. And we use the same procedure. So I'll let you read that. You should try to do it yourself before you read what's going on here. But now, notice that this exponent of t is I plus j mod n. Okay. But once I make the but we're taking the exponent mod m, and so by this business we did earlier, we can drop the mod n, and it looks like this. So this is the reduction of this product of three things. If we associate differently, you can go through the same algebra here. This is just pushing exponents around using this formula. So it's not deep mathematics. It's just a little unpleasant, I guess you might say. And you will come out with exactly the same thing. So we have associativity. We have identity. We have associativity. We need also to verify that every element, a to the I, b to the j of G, where I and j are in the appropriate range, has an inverse. So we have to solve this equation. 1 equals a to the I, b to the j, a to the x, b to the y. We have to solve this for x and y. And this is the product formula. This will hold. This will equal 1 if and only if both exponents are 0. Okay. So I plus t to the j x here has to be congruent to 0 mod m, and j plus y has to be congruent to 0 mod n. Well, the second of these equations is easy to deal with. Y has to be negative j mod n, which is the same as n minus j mod n. As to the first equation, we can first write this as t to the jx congruent to negative I mod m. And now we can use the t condition and to avail ourselves of the t condition, we need t to the power n. So multiply both sides by t to the n minus j. Okay. And that will give us a t to the n here, and mod m, that's 1, so I'm just going to be left with x here. And on this side, negative I t to the n minus j. So these are congruent mod m. And I have x and y now, and just to do a quick check in case we screwed something up, we can actually take this as the inverse and just multiply, make sure everything works okay. And I'll let you take care of that. So G is a group of order Mn, and the basic commutativity rule holds. What remains to verify is that the order of A is M and the order of B is N. But since the elements a squared, and so on up to a to the m minus 1 are distinct and not equal to the identity, and similarly for these elements, we know that the order of A is at least M and the order of B is at least N. Now, to show that the orders are precisely M and N, and for other reasons, we need to take a closer look at the formal symbols in the underlying set. For example, A superscript I. This is a formal symbol. It's not a product of A with itself I times. To denote that product, I'm going to write A star I temporarily. So this is by definition this product. This is the formal symbol A superscript I. And it's not terribly difficult to show by induction that when I is in this range, these two are equal. And so the formal symbol A superscript I is in fact the product of I copies of A, and so we can drop the asterisk I and think of A superscript I either as the formal symbol or at which happens to be equal to the product of I copies of A. So as far as the proof, certainly this is true for I equals 1 because both sides are A to the 1. If it's true for a given I, then when we look at A star I plus 1, that is the product of I plus 1 copies of A. So that's A star I times A. And the inductive hypothesis tells us this is the formal symbol in the underlying set, AI, which, by the way, is an abbreviation. AI is really AIB0, right? Okay. So this is AI times A. Now we use the product formula, the definition of star, to multiply AI by what is A1, A superscript 1, and we get A to the power I plus 1 mod M. And so I broke this into two parts. When I is M minus 1, I plus 1 is M. All this in the exponent here is 0, and I get A superscript 0, which is the identity in the group. And otherwise, if I is less than M minus 1, we just get A to the I plus 1. This is the formal symbol AI plus 1. And this is the product of I plus 1 copies of A, and they are equal in this case. Excuse me. So for I between 1 and M minus 1, we can say that the formal symbol A to the I is the same as the product of I copies of A, or maybe we should say it the other way around. The product of I copies of A is equal to the formal symbol A superscript I. And since A star M, this is the product of M copies of A, is equal to 1, the order of A is less than or equal to M, but we've already seen it's greater than or equal to M, so it is equal to M. And a similar argument, analogous argument, works for the element B. Its powers, if you take the product of J copies of B, it's equal to the formal symbol B superscript J. This means we can get rid of the asterisk and just use juxtaposition for the product. Because when we look at this with I and J in the appropriate range, we think of that as a formal symbol in the underlying set, but now we can think of it as a product of I copies of A followed by J copies of B. Well, in summary, the standard template is valid if and only if the T condition holds. And when this condition holds, we will refer to T as a valid T exponent. A valid standard template defines an essentially unique group, G, with this underlying set and this group product. Now I'm using juxtaposition to denote the product. So if you saw this for the first time, you'd have a right to say, well, gee, this looks like the product's already going on here when all you've done is to find the underlying set. And my response would be, well, treat these as formal symbols for the time being. Then this makes sense as a set of formal symbols. And define this product on these formal symbols, and then you will see with a tiny bit of work that in fact the formal symbols are equal to the product you think they should be. Here's a formula for the inverse of one of these elements of the underlying set. And I'll let you derive that formula. Example. Let's look at this standard template. TM2T, so N is 2 here. Group has order 2M, A has order M, B has order 2, and here's the basic commutativity rule. This is valid if and only if the T condition holds. T to the order of B, which is 2, congruent to 1 mod order of A, which is M. And as I mentioned before, we can assume that T lies in this range. One solution to this congruence is T equals M minus 1. And all you have to do is plug into here. M minus 1 quantity squared will be congruent to 1 mod M. And that gives this template. Everything's the same here, but I put M minus 1 here for T, and I'm calling this D sub 2M for a reason you'll see in a moment. We saw in example 613 for the case D8, and we'll verify in general, that this is the template that describes the family of dihedral groups. So when M is 4, we get D8 here. This is a group of order 8, one element of order 4, one of order 2. This is the rotation, so we're talking about the square now, rotation of 90 degrees, reflection. So this example of a standard template, when N is 2, defines all of the dihedral groups, the family of dihedral groups, depending on the value of M. And so that's why we refer to this. Since we know now that standard templates define unique, valid standard templates define unique groups, we know that these templates uniquely determine the dihedral groups. So we can call this template the dihedral template. And there's really one dihedral template for each value of M, so it's a family of dihedral templates. You may recall our earlier discussion concerning the motivation behind defining groups. And one of our motivations on the theoretical side was to determine all groups of a given order. And I mentioned that we're going to accomplish this feat for groups up to order 15, and that order 12 would give us the most trouble, by far, actually. We've encountered two cyclic groups of order 12, as I discussed. I got to fix this typo here. We've talked about the dihedral group D12, which is the group of symmetries of the hexagon. And we have talked about the alternating group A4, which has order 4 factorial divided by 2, which is also 12. the fifth group, I mentioned there were 5, the fifth group of order 12, where does that come from? Well, a standard template. It is defined by a standard template, and it's this one, T34 little t. Order 12, order of A3, order of B4, and the commutativity rule. Now, when is this valid? If and only if the t condition holds, which is t to the fourth congruent to 1 mod 3. And t lies in the range from 1 to, well, up to 2, actually. So t has to be either 1 or 2. But the template T341, when t is 1, is abelian, because the commutativity rule now becomes BA equals AB. And this then defines a unique abelian group of order 12. Moreover, actually there are 2 of those, so we have to figure out which one is defined by this template. But because the order of A is 3 and the order of B is 4, and 3 and 4 are relatively prime, and commute, the order of the product is the product of the orders, which is 12, so G contains this, the unique group defined by this template contains an element of order 12, therefore the group is cyclic. So this uniquely determines the cyclic group of order 12. And that's here. The other template, when t is 2, gives us a group of order 12, order of A is 3, order of B is 4, but this is now the commutativity rule. So A and B do not commute. This is a non-abelian group of order 12. It is, in fact, the fifth group of order 12. Now, this requires proof. All we know at the moment is that this is a group of order 12, uniquely defined by the template. It's clearly not one of the abelian groups, because this group is not abelian, but it's not immediately obvious that it's not A4 or D12. So I'm going to leave that for you to ponder. Why is this group not isomorphic to either A4 or D12? And as you know, one way to approach this issue of showing two groups are not isomorphic is to find an isomorphism invariant that holds for one of the groups but not the other. Now let's take a look again at template equivalence in the context of standard templates. By definition, two standard templates are equivalent if they define the same group. And here's a simple example. This template, TMNT, is a standard template with basic commutativity rule. This template is a little different. The group order is the same. The generator orders are the same. But the commutativity rule looks quite different. And I'm going to leave it as an exercise for you to show that these are in fact equivalent templates. And I'll give you a hint in the exercises. This is in fact also a standard template. But there are other standard templates that are equivalent to this template TMN_t. And so they define the same essential unique group. To see this, let's suppose that G fits this template, TMNT. If we said beta equal to b to the k, where k is relatively prime to the order of b, so that's n, then Bezo's identity tells us that there are integers u and v for which uk plus vn equals 1. Therefore, we know that beta equals b to the k by definition, but b is equal to b to this power 1, uk plus vn, and since n is the order of b, this is equal to b to the uk, or b to the k to the power u, that's beta to the u. So these two equations tell us that each of b and beta uniquely determine the other. And also that the group G, which is generated by A, B, is also generated by A and beta. Moreover, the order of beta is the order of b to the k, and by the well-known formula for the order of a power, this is, and since order of b and k are relatively prime, this is the order of b, which is n. So beta is also a generator with A, along with A, is generator of G, and it has the same order as the generator of B. Also, this commutativity rule, the basic BA equals A to the TB, implies that beta A equals B to the KA, and we use the general commutativity rule to get A to the T to the K, B to the K, which is A to the T to the K beta. And so the group G also satisfies the standard template where the T value is T to the K, generated by two generators, A and beta, group order Mn, order of A M, order of beta N, and the basic commutativity rule with exponent T to the K. That tells us, by the way, because this template is valid, since the group G satisfies this template, that the T condition holds, but you can check that easily directly from the T condition for the other template. So these two templates are equivalent as long as K and N are relatively prime. And here is the theorem to that effect. Another way to try to remember this is that you can replace B by B to the K and get an equivalent standard template if B to the K generates the same cyclic subgroup as B, because that's equivalent to saying that K is relatively prime to the order of B. Let's take a look now at what is actually quite an interesting example. Later in the book, we're going to analyze the groups of order PQ, where P and Q are distinct primes, and we can assume P is less than Q. And for this analysis, we're going to consider two separate cases, namely when P divides Q minus 1, and then when P does not divide Q minus 1. In the former case, P divides Q minus 1, these standard templates play an important role. This is T, QP little t, two generators, group order PQ, order of AQ, order of BP, basic commutativity rule. These templates are valid for every T in this range. We can restrict to this range without loss of templates that satisfy the T condition, which looks like this. P is the order of B, Q is the order of A. Now, another way to express the T condition is to say that T belongs to this group, ZQ star. Remember, that's the group of all positive integers less than Q and relatively prime to Q. And since Q is prime, that's all the integers from 1 to Q minus 1. And because of this, this now says that T to the P is equal to the identity 1 in this group, because the product in this group is multiplication mod Q. So this equation says either T equals the identity, 1, or the order of T is P. And that's because P is a prime, so if P is an exponent of T and T is not the identity, then P is actually the order of T. Now, we're going to prove in Chapter 7 that ZQ star is actually cyclic of order Q minus 1. So let's say it's generated by alpha. Well, the theorem that we had in Chapter 2 tells us precisely which elements of this group have order P. So the order of alpha to the k is P if and only if k is a multiple of Q minus 1 over P, where R ranges from 1 to P minus 1. So the valid T exponents have this form. They are alpha to this power, R times Q minus 1 divided by P. And I'll call those T sub R. Well, when R equals 0, we get the, so this, I should have, I did say, okay, for R ranges from 0 to P. When R is 0, T sub R is 1, and so the template defines a unique abelian group of order PQ. And that is, in fact, the cyclic group of order PQ. We used this argument earlier. I think the orders were 3 and 4. Okay. The product here, AB, has order PQ, so it's cyclic. On the other hand, since every value of R in this range is relatively prime to the order of B, the previous theorem tells us that all of these templates are equivalent. And so they all define the same non-abelian, the same unique non-abelian group of order PQ. And that's very significant. And so I put it in a theorem for later use. Let P and Q be prime numbers for which P divides Q minus 1. Consider the standard template. If the group ZQ stars generated by alpha, then the valid T exponents are these. This template with T equals 1 defines a unique abelian group of order PQ, and it's cyclic. The other templates, the valid ones, are equivalent, and they define a single non-abelian group of order PQ. Okay. And that's going to be, as I said, very significant in determining all groups of order PQ. So finally, in this chapter, I want to discuss something I said I would discuss earlier. While the notion of a group template is not standard, I've not seen it elsewhere. And I hope by now our discussion of group templates helps you believe that they are, in some sense, useful. In any case, there is a standard concept that is similar to, related to group templates, and it's called a group presentation. This is a standard concept, but it tends to be treated only in more advanced books and courses on group theory. I would say graduate level courses. I'm not going to discuss group presentations in this book. Maybe I should, I don't know. But I decided not to. Except I do want to make a couple remarks right now. Group presentations are similar to group templates with a critical exception, and that is the relations between generators must have this form. W equals 1, 1 is the group identity, and W is a word over the generators and their inverses. W is called a relator. This is called a relation, and W is called a relator. So you can specify, and you do specify generators, and you specify relations, or equivalently relators, because you always stick an equals 1 after each relator to get the relations. Now the point here is that no non-equalities are allowed in a group presentation, and therefore there's no way to specify the order of any elements, because the equation order of A equals n is really shorthand for one equality and one non-equality. A to the n is 1, A to the n minus 1 is not 1, and this is not allowed in a presentation. You also can't specify the order of the group. All you can do is specify relations, or the corresponding relators. So these rather severe restrictions limit the flexibility of group presentations, but they do imply that all group presentations are valid, because we can always take every generator to be the identity, and then every relation collapses to 1 equals 1, which is true. So the trivial group satisfies all presentations, and we don't have to worry about validity and invalidity as far as group presentations are concerned. The trick, of course, is to determine whether or not a given group presentation defines a non-trivial group. We don't much care about presentations that only define the trivial group. Now, although we haven't discussed normal subgroups, they are important in the study of group presentations. So let me at least give you some words here that may or may not make any sense. The best hope for getting a non-trivial group with a given set of generators, call it X, and a given set of relations is to start with the free group on X. So it's the free group generated by X. And then form the quotient group of G, which we also haven't discussed officially. We talked about quotient groups in general terms for widgets. You form the quotient group of G with the smallest normal subgroup generated by the relators. Relations are equations, but relators are words over the generator, so they're actually elements of the group. So we can take the subgroup generated by the relators, but you cannot take a quotient group by a subgroup unless it's normal. And this we will discuss carefully at the appropriate time. So you have to take the subgroup generated by the relators and perhaps kick it up a little bit to a normal subgroup. So you want the smallest normal subgroup that contains the subgroup generated by the relators. Okay. That's called the normal closure of the subgroup generated by the relators. So I presume much of this didn't make absolute sense, but you get some feeling for what's going on here, and also why this topic is not usually covered in elementary group theory textbooks. So because I called this book a comprehensive introduction to group theory, I thought maybe this would be a little too much. I can't remember. I think I define normal closure later on in the book, but I don't really discuss it in any detail. So there you have it. Group templates are non-standard ideas that you may not find anywhere else except in this course, but group presentations are ubiquitous. They're very important concepts in group theory.